Here we're setting dependencies, that is how every activity affects other activities, that is what it supplies to other activities and what it requires from other activities. Here we're considering equalization in an electronic product, and we're looking at the whole set of activities and asking the question, how highly does equalization depend on the highlighted task? And as you move through, you just click the button high, low, or none, and you that way form a connection to this product, and then you'll go on to the next item and you ask the same set of questions again. To move through a typical program through this set of screens for each activity typically takes about a morning or an afternoon. It's a fairly solid activity and probably should be done in one sitting if you can do it, and preferably with the whole team, as it keeps the whole thought pattern together. You don't forget what you've worked through previously. Once you've done the interconnections, you've worked through the prior slide, you wind up with a loaded matrix, and you can look at the matrix, or you can actually look at a diagram which shows a network both forward and reverse, which is very instructive. You start to see just the real complexity of your program. But a really neat thing to see here, if you remember the MIT break case, the matrix for that we had, and this is the same matrix by the way, but just has been entered through Project DSM. What you see is that Project DSM removed all of the clutter automatically. Instead of having loads of stuff up in the right hand corner of the matrix here, which was caused by the fact that you had loads of ineffective or badly timed feed forwards and feedbacks, or in this case feedbacks. Timing of your dependencies was poor, and that structure then led to a great deal of inefficiency, and each one of those nodes represented information that wasn't ready when it was needed and would in effect cause a potential delay, problem, or crisis, and they just migrate across into the main program. Well, what the Project DSM is doing is it is simply removing all of that as it goes. Each time you put in an interaction into your table, it continually reruns the loop, looks at the program, and optimizes. So it's in a state of continuous optimization as you're entering the data. So by the time you get to the end of it, you're just left with the chicken and eggs that really can't be removed by a simple sort process. And of course then you have to act on that, and that's what the little table in the bottom corner indicates. That going back to our chart, we had all of that stuff up in the right hand corner. Project DSM simply always delivers you the clean picture. It's done the sorts, and you're really looking at just that last one. It's been improved by say 4 to 1 or more relative to typical process. Here we see a pink area, and this is an area in, again, the break case, which is highly interactive. Everything in this depends on everything else, so that if we had a failure here, this whole pink block is highlighted as a potential rework block, and as such what we want to do is to try and pick the one point in this highly interconnected web or Gordian knot. Pick the one point that you pull and the whole knot falls apart, and you wind up with a simple, clean, under-diagonal program. More often than not that doesn't occur, but you can simplify them greatly. What you do here is that you go in and ask for advice on how to optimize this, and what you can see is that if you have to rework in this sequencing advice, at the top it takes that block and it says, okay, we have a rework effort that would be 284 man days, and rework costs in this case of about $41,000 or thereabouts. And so the other thing is that you can have an optimization objective, either the size of blocks, the complexity of the program, rework cost, or rework effort, and that is days to completion or days to get through the rework. So you can choose to optimize in one of those ways, and we chose to re-optimize rework cost here. And it comes up with a suggestion, and the optimal one is put at the top of the list for you. And you may know better and choose one of the other ones because you know more about it or you find it easier to execute. But it will suggest something, and here it's saying if you simplify by making an assumption on the customer feedback on options, depends on the terms and conditions of use. If you can provide an assumption between those two items, you can reduce complexity by 98%, cost by 86%, and effort by 83%. Now, an example of that is back in the brake case, and you can see the pink area behind the two purple boxes here, and that was the original interaction or potential rework area. And by making an assumption where the red circle is, you can actually simplify this down to the two smaller boxes, which is a significantly reduced rework area. It also is probably easier to manage because instead of having one complex activity there, we've got two fairly focused activities, one being kinematics or the mechanics of the brake system, the other being the thermodynamics. The lower one is the thermodynamics, how we get rid of the heat once the braking system has worked. And because these little purple boxes are so interactive and so tightly coupled together, in terms of managing this, we're probably better with a co-located team. That is, that the people working on this program will probably be in one area, either virtually or physically, and there's a lot then of communication, informal communication, exchanges, walking over, looking at each other's problems, etc. And so with that level of tight communication, the dense intercommunication network that's represented by this personal block is much easier to manage. You'll get more effective results that way. The same is true once you get down to the thermo part of the operation. It again is a quite interconnected operation, and as such you're going to probably use co-located teams again there. And given that you're handing off between these teams, that the mechanics are sorted and you're handing off between them, it's a great place for review where the activity drops to zero between them. It is a natural place for a review. And so you're not doing your standard review process. All you're doing is timing it to the natural places inside the program as to where reviews would really fit. And they fit well. You're not, in the case of Team A, trying to do make-up work to get into a review, and on the other side of it you're not having to accept a relatively lousy structure as your inputs if you're the thermal team, because the review was earlier than the guys in Team A were ready for. So the timing then gives you again efficiencies. The structure of the organization is matched to the DNA of the program, that is, its information flows, and you wind up with an optimized project execution plan, and with necessarily an optimized physical structure for the organization and review process as well.